Studying the many intangible objects millions of light years lost in space might seem like a hard nut to crack. However, supermassive black holes have provided our genius astronomers with a brand new avenue of inquiry into the high class of inaccessible, far-off objects. The most tightly packed of these space discoveries are black holes, some of which can be found inside a living star. A relatively brief but quite instructive burst of light can be seen when stars are torn apart as they approach supermassive black holes. If we know where to look for and how to interpret these star-destroying events, we might get lucky enough to locate the enormous black holes in the universe. Let's explore the various ways we can see black holes, and in particular, what we know and don't know about how these creepy dark space objects can disturb stars. A black hole is an object in the cosmos with an incredibly strong gravitational pull from which nothing, not even light, can escape. A huge star's demise can result in the formation of a black hole. Only stars with a mass greater than 3 solar masses eventually collapse into black holes. Smaller stars develop into less compact bodies, such as neutron stars or white dwarfs. It is pretty difficult to look right at the center of our galaxy, which is the Milky Way, in addition to the fact that it necessitates cutting through cosmic dust, which absorbs visible light. There's also a terrifying monster in there. For staring that beast right in the face, 2 scientists, Andrea Ghez and Reinhard Genzel, were awarded the 2020 Nobel Prize in Physics. To get a clear image of what's happening at the Milky Way's core, these scientists created tools and techniques. They discovered a cluster of stars there and observed their motion for more than a decade. Now that's a long time. During this time, the stars appeared to revolve around a point in space as though they were subject to the gravitational pull of up to 4.5 million suns. However, nothing was emitting any light at that location in space. What kind of thing would have 4.5 million suns worth of gravitational pull and not emit any light? Only a black hole would, and not just your regular black hole, but a supermassive black hole. Indicating the locations of the stars for each year between 1995 and 2008 are circles around the stars. An unseen central object, which has a gravitational pull of 4.5 million suns, can be seen orbiting the stars. Due to their enormous density, black holes are so small that they might be created by compressing the entire Earth to the size of a ping pong ball. With a mass of 4.5 million suns, the black hole at the center of the Milky Way might fit inside Mercury's orbit. Such a monster is not the only one the Milky Way galaxy is hiding. Supermassive black holes, which can be as huge as 100 billion suns, are thought to be at the heart of all giant galaxies. We don't know how the universe creates such enormous things, but even more perplexing is the observation of supermassive black holes in the early universe, when the universe was much younger than it should have been for such black holes to develop. It is difficult to detect black holes since they are essentially invisible and do not emit any light, making them very difficult to study. Only the nearest galaxies may use the technique that was used to identify the supermassive black hole at the heart of our galaxy, measuring the motion of stars around it. Beyond those, not even the most advanced telescopes can distinguish between individual stars moving in the galactic core. There is another way to see black holes from a greater distance. About 10% of supermassive black holes are surrounded by gas that progressively falls onto them. The gas travels like water down a drain as it gets closer to the black hole, speeding up and speeding up fast. Black hole gas can travel at speeds so fast that it glows and heats up. Recently, similar light was used to photograph the silhouette of the supermassive black hole at the galaxy M87 center. In actuality, the brightest source of light in the universe is gas that is about to descend onto a supermassive black hole. Supermassive black holes can be located using this light, and their mass and spin can also be determined. What happens with the other 90% of supermassive black holes which do not currently have gas flowing into them? We are entirely blind to these black holes, unless, and this is a very uncommon unless, a star unlucky enough to be nearby the supermassive black hole experiences a tidal disruption event, which occurs only a few 100,000 years in a galaxy, TDE. The moon's gravitational pull on the Earth's surface, which is stronger on the side of the planet that faces the moon than on the other, is what causes tides. The unlucky star will experience a higher gravitational force on the side that is similarly facing the black hole. Additionally, all stars are held together by gravity. Accordingly, if a star approaches a black hole closely enough, the gravitational forces pushing on its opposite sides may be greater than the forces holding it together. The star will then get spaghettified or stretched out into a lengthy thread. To help you wrap your mind around the situation, imagine falling into a black hole feet first. Your feet are sucked in more quickly than your head because they experience a larger gravitational pull due to their proximity to the black hole. Your entire body will start to swell as a result of this reaction. In the event of a star, it splits in half, with half being ejected into space and the other half entering orbit around the black hole. The half star that remains in orbit around the black hole will move faster, heat up, and radiate light as it gets closer to the black hole. Just like the gas around active black holes, but unlike active black holes, which continuously emit light due to their abundant gas supply, a single disrupted star's brightness will dim after a few weeks or months once all the material from the circulating half star has fallen into the black hole. You might consider this to be a feast, but it is only a snack in the eyes of the black hole. Has this happened before? Oh, yes, it has. Astronomers have found black holes that have destroyed stars, and this discovery has helped them understand how supermassive black holes are created. As a helpless star was being spaghettified by a black hole, astronomers made the discovery. The star ventured too close to the intermediate-sized black hole, which is situated 850 million light-years from Earth in the galaxy SDSS J152120.07 plus 140410.5, snared and destroyed the star, emitting a strong beam of light that allowed astronomers to find it. The Young Supernova Experiment, a 3-year scan of the sky using Hawaii-based telescopes that look for transient flashes from cosmic events, like supernova explosions, let scientists find the flare. Named AT220NEH, the discovery was discussed by the researchers in the journal Nature Astronomy. They had a unique opportunity to see what would have otherwise remained hidden from us, since they were able to photograph this mid-sized black hole as it ate a star. Furthermore, we can learn more about this elusive class of middleweight black holes, which may make up the majority of the black holes in the centers of galaxies, by studying the flare's physical characteristics. To aid your recollection, we'll go through the specifics once more. Black holes eat, and the way they eat is very destructive. A phenomenon known as tidal disruption event happens when the strong forces from the black hole's gravity act upon a defenseless star, which is created when a black hole swallows a star. A star that has been drawn toward a black hole by its gravity will be drawn closer and closer to the ravenous giant's gaping mouth before being stripped of its outer layers and stretched as it sinks inside. The star is turned into a long, noodle-like strand of heated plasma as a result of this process, which tightly twists the black hole like spaghetti around a fork. The process accelerates the plasma, which spins out into a massive jet of energy and matter that emits a recognizable, brilliant flash. Then, astronomers can use optical, X-ray, and radio wave telescopes to find this flash. The recently discovered black hole is unusual because it belongs to a class of black holes with masses ranging from 100 to 10,000 times that of the Sun. It is intermediate in size. These middleweight singularities, according to scientists, eat stars, gas, dust, and even other black holes before becoming supermassive black holes. Long trains of matter whirl in orbit around supermassive black holes, which are frequently millions or even billions of times more massive than the Sun. But it is yet unknown if these trains originate from intermediate black holes, according to a certain theory. Dwarf galaxies that developed from intermediate black holes in the early universe were numerous and eventually combined to become the larger galaxies and black holes we observe today. Astrophysicists need to determine the precise number of middleweight black holes to determine whether this idea is true. As we find and analyze more TDA, we hope to also use them as tools for examining the monsters that lurk at the center of every galaxy.